Hello. Okay, this is a video on finding the derivatives of exponential functions. Just gonna write the title, exponential functions. Okay, so we did this in class on Friday and today, Monday. But a bunch of people are away here and there, so let's just summarize what we did. So we started with this cool guy, f of x equals e to the x. So we started with that exponential function. So e is just this special number, Euler's number. And it turns out that it's the number, it's a special irrational number, just like the number pi. It's this non-terminating decimal. And you can actually find the value of e by calculating the limit as n goes to infinity of 1 plus 1 over n to the power of n. So as you sub numbers in for n that are bigger and bigger and bigger, so start with 1. 1 plus 1 over 1 to the power of 1 equals 2. Then try it with 2, 3, 1,000, 2 million, whatever. Just keep finding bigger and bigger numbers of n, and you'll see that the value of e is approaching 2.718 and etc. I can't remember. But there is an e button on your calculator, and if you click on that, it will tell you what the value of e is. Okay, so we're just exploring what the derivative of e to the x is, and also what the derivative of any exponential function is, like 2 to the x, 3 to the x, 4 to the x, whatever to the x. So we proved this using first principles in class. So the limit as h approaches 0 of f of x plus h minus f of x over h. So we used that in class to prove that the derivative of e to the x is actually just e to the x. Crazy. So, yeah. If we want to look at the graphs of e to the x, passes through 1. It's got an asymptote at y equals 0, and looks like your basic exponential function. So that's our graph of e to the x, and its derivative is the same thing. Awesome. So then we went on and we looked at, well, what about the derivative of any function, any exponential function? So like 2 to the x, 3 to the x. So we're just going to say b to the x, where b is any number. 2, 3, half, quarter, whatever. So we used first principles again in class, and this time we were going to do an investigation, but we ran out of time. So we used first principles, and then we kind of just approximated what the slope would be to help us figure it out in the end. And we found out the derivative of b to the x is just b to the x multiplied by ln b. So yeah, that's what we found out was our exponential function's derivative. And I should mention that e to the x, technically, its derivative is the same, e to the x ln e, so same thing as our exponential function, but it turns out that ln e, if you think about our logarithms, technically that's ln is log base e. That's what ln stands for, so it's the natural logarithm, so it's got a log of base e, so that's in fact equal to 1, right? Because it's like e to the 1 is equal to e. Remember, that's our base, that's our exponent, that's our answer. Or sorry, just kidding. That's our base, this is our exponent, that's our answer. So e to the 1 equals e. So, turns out this is actually just equal to 1. So that's why we just say the derivative of e to the x is e to the x. And then the derivative of b to the x is b to the x ln b. So finding the derivatives of these isn't too bad, except you also have to factor in that sometimes you need to use the chain rule when finding the derivative. So for example, if your function was e to the, instead of just e to the x, let's say it was e to the g of x. So say you had some function, I'm just calling it g to the x. So it could be like x squared or 3x plus 2. So you have some function in your exponent. When you go to find the derivative of that function, your derivative would still be e to the x, or e to the g of x, and then you'd have to multiply that by the derivative of g to the x. Okay, and that's the same thing for our exponential function. So if you had some kind of function like b to the g of x, and we wanted to find the derivative, we'd have to find the derivative of b to the g of x, which is just b to the g of x ln b, and then we'd have to multiply that by the derivative of g of x. Okay, so let's just do a quick example so you know what I'm talking about. Example. So let's say we wanted to find the derivative of e to the 3x. So to find that derivative, we just follow our derivative rules. So the derivative of e to the x is just e to the x. So we just write e to the 3x, and then we multiply it by the derivative of the inner function, which is 3x. So the derivative of 3x is just 3, so we can write that as 3 e to the 3x. And then, if we wanted to find the derivative of, let's say, 2 to the x squared. So if we find the derivative, we just follow our derivative rules. So we just make it 2 to the x squared ln 2. And then we got to multiply that whole thing by the derivative of the exponent, and the derivative of x squared is just 2x. And you can't really simplify that, because ln 2 times 2x, like, you're not going to simplify that at all. So let's just try one crazy one. So let's say you had f of x equals x times 3 to the 2x minus 5. So let's say that was your function. So if we had to find the derivative of that, we're going to have to use product rule, because technically we got this function times by this function. So if we're using product rule, got to find the derivative of the first function, so that's just 1, multiplied by the second function, so 3 to the 2x minus 5, plus, we just write the first function as is, so x, then we find the derivative of the second function, so the derivative of 3 to the 2x minus 5 is 3 to the 2x minus 5 ln 3 times the derivative of 2x minus 5, which is 2. Which looks kind of crazy, so if we just simplify that, 3 to the 2x minus 5 plus 2x ln 3, 3 to the 2x minus 5. And we should always factor if we can. So if you look at what they both have in common, they got this and this in common. So let's factor out a 3 to the 2x minus 5, and we're left with 1 plus 2x ln 3. Easy peasy. Okay, bye.